At the deepest level of computing, there is no code. There is only a mechanical flow of physical data through silicon. To see how software actually executes, we have to look past high-level syntax and visualize the runtime system. Take a simple method call, like d.bark. Most developers read this as an object performing an action. They see the instance d as the owner of the bark behavior. But there are no methods inside objects. Execution is a pipeline that routes memory pointers into physical CPU registers. Stripping away the syntax to see this pipeline is where you stop memorizing Python rules and start understanding how the interpreter manages the machine. We begin by freezing the execution environment to map the state of memory before the line runs. On the heap, we have the dog class at 0x1000, the bark function at 0x2000, and instance d at 0x3000. Inside d is a reference count and a type pointer, connecting it to its parent class. Processing .bark triggers a search for executable code. The interpreter follows the type pointer from the instance directly to the dog class. This descriptor protocol forces a lookup of bark inside the class dictionary, revealing a function pointer targeting the code at 0x2000. Attribute access is a navigational procedure to locate static code. The function exists as a separate entity from the instance's memory. The interpreter now has the code and the data, but they are still disconnected. It needs a way to pair them. To bridge this gap, CPython creates a temporary structure in memory called a bound method, located here at 0x4000. The func pointer slot locks onto the address of the bark function at 0x2000. Simultaneously, the self pointer slot locks onto the address of instance d at 0x3000. This structure is nothing more than a transient pair of pointers. This temporary block is the only place where the function and instance are linked. They never actually merge within the heap. The bound method exists only to transport these two addresses into the next stage of execution. When we add the parentheses to the call, we move from preparation to execution. This triggers a PyFrame object, a C-level structure holding the state for the call. Inside is a local slot, f_locals+0, currently undefined. To map arguments into this new frame, the self pointer, address 0x3000, is copied and routed directly into that first local slot. This is the exact microsecond when self is created. Self is not a variable passed by the user. It is a pointer the runtime injects into the frame's memory. It is just a memory address waiting in a slot for the hardware to use it. Now that the frame is staged, the interpreter begins executing bytecode. The first instruction, load fast 0, tells the interpreter to move the value in the first local slot toward the processor. At the hardware level, this maps to a move instruction. The pointer, address 0x3000, is copied into the CPU's high-speed RAX register. The physical hardware now has the direct address of instance D. Only now can the CPU perform logic, using that register to access and manipulate the object's data in the heap. The entire Python interpreter stack is a system designed to hand off this one memory address to the CPU. When we view the entire trajectory, we see a single path of data flowing from the heap into the hardware. It confirms that objects are just passive data storage, and methods are temporary illusions created by the runtime. Code execution is better understood as the injection of pointers into frame slots, rather than an object doing something. This is the perspective needed to troubleshoot memory leaks in C extensions, or to understand how an interpreter is built from the ground up. Seeing the system as a series of data flows and pointer transformations allows you to move between different languages and architectures with more clarity. It is the same mechanical logic that allows machine learning frameworks to move large tensors across distributed memory. From here, you can explore how modern Python versions use vector call to skip this entire overhead and execute even faster. You are no longer just tracing Python code, you are seeing how programming languages are constructed to route information through a machine.